what we do now is we want to look a little bit more into, is there more than just the simple tricks on the coding matrix? And here we have something new, what is called Fulcrum, right? The idea was, can we do a little bit more? And what is missing for us currently, and what was one of the pain points, is how much can we code, recode? So what is the field size that we can use? What can digest a certain element? So you know maybe that there's some heterogeneity in the devices, but not only in the end devices, also in the network components. And if you see that you have some big server farms here, you have also switches, access points, and then you have devices down here, then you must ask, if I do encode, recode, decode, they should do it on the same field, right? We always use the same. So now, if you ask everybody what kind of field size can you calculate, then you see that, oh, here we have maybe a field size 2 to the power of b possible. The switches, even though they're very powerful, they have only the possibility to do binary recoding, because they would say there are millions of streams. It's so complex, the recoding, maybe I don't want to do it in a higher field than binary. And you don't have to ask the others, you're already doomed. Because if one in the chain will say binary, it's binary. And that is not very nice. So what we would like to do is to say, why don't we just make a code that allows us to use different fields? So the encoder and the decoder maybe will do the same code, but not necessarily. And the recoder can do a totally different one. So how is this possible? So what we built here in the center is to say we make two types of codes, an inner code and an outer code. And the network can then decide, will I work on the inner code, or do I have more resources to also use the outer code? So we do a recoding on the inner code and then recoding over the outer code. And in the back, we could say, okay, what can we decode? Inner code at least, or also the outer code? And it doesn't need to be that we decode everything what also the source had. But if we only can decode that one, maybe we will not get all the data. So how does it work? What we take is, we take the original symbols, make an outer code, and then based on that, an inner code. A better view is here. You see here the matrix. You have packet 1, 2, 3, 4, and 5. And then you take, okay, packet 1 is in the coding matrix here. It's a systematic code. Then you have packet 2, 3, 4, 5. This is the packet here. And this is what the inner code looks like. And now on the outer code, you take coefficients over all elements. You put them here, and you have now a code over all the things as you know it. So this one is systematic, and here's something, it is full-blown code, so to speak. And then you can see how many packets in the inner code I really would like to use in the outer code. And you can see this is the standard GF2 is here. Now, if you take the Fulcrum code, you can bring up the decoding probability to this end, which is quite nice. And this is the number of extra coded packets. And you have seen this plot before, right? When we ask what is the extra of the binary code. Now we combine a binary code together with a higher field code. If you then combine this Fulcrum code with certain parameters R, which has to do with the elements of the outer code, then you see this is the decoding probability for the Fulcrum code, and down here is the Raptor code. Raptor code is what Qualcomm has, right? But this is not really a network code. This is just an end-to-end code. But it's a rateless code. It's like Reed-Solomon, but rateless. And then they also have some decoding probabilities, but you see here that Fulcrum is way better than this. Now, here are some results that shows how good the encoder and decoder works, right? What you can do with this. The interesting part is really that with the Fulcrum, you enable heterogeneous coding in the network. So depending on the complexity, it's like liquid complexity. Whenever you can do something more, you will invest it. What I did not show here, maybe we will have one colleague that can come to explain this a little bit more in detail. The nice thing is, if you take 2 to the 8 and, for the encoder and 2 to the 8 for the decoder, and you switch the recoder for binary or 2 to the 8, the performance in the end is not so much different. It would be different if everybody would be binary. That is a problem. But just the fact that you have the outer elements like encode and decode already in the higher field, the recoding with binary is not that bad. It's not so much punishment in that, okay? We will have a look into this. You can even use this for heterogeneous receivers, as I said. So as if you can decode the inner and outer code, you will get more out of it. But if you only can decode the inner code, also fine. If the losses are not too high, as you can see here, then you can also take packets out of that.